Hi, everybody. As we continue to talk about thermodynamics, one of the more interesting topics is heat engines. These are devices that convert thermal energy to mechanical energy. Usually they're just called engines. You know, a steam engine on a train, the engine inside your car, those kinds of things are what we're talking about. Anything that uses heat and turns it into mechanical energy usually in the form of a spinning wheel or a spinning shaft or something like that. So how do these things work? Well, the basic idea is this. We've got a source of heat, and as you know, heat is energy. Notice the symbol we use for heat is Q, because we're talking about energy, not temperature here. Okay, so that's the heat. It goes into the engine. Okay, so that goes in. And what does the engine do? Well, among other things, as you know, it gets hot, and then it releases that heat to the environment. If you don't believe me, just put your hand on a tailpipe of a car that's running. No, don't do that. That would be stupid. Trust me, it's really, really hot. So heat comes out, but the heat that comes out is not as much as the heat that went in. The difference between the two is the work that's done by the engine. That work is what causes the engine to move. That source of heat is called the heat source. Okay, that was pretty easy. The place where the heat is released to, down here where it says cold, and by the way, cold is still hot enough to burn your skin in the case of an automobile engine, is called the heat sink. And so lots of heat comes out of the heat source, some heat goes into the heat sink, and the difference between the two tells you how much work is done by the engine. Got that? The work done, as I just described, is the heat that goes in minus the heat that comes out. And so if we want to define efficiency, we can define the efficiency as the work that you get from a machine, which is what you want, divided by the energy that you put into the machine. That's Q sub H. And then times 100% to turn into a percent. By substituting this expression right here into the equation, in place of this numerator, then it becomes QH minus QC over QH. The QH over QH is 1. So it's 1 minus the heat that goes out divided by the heat that goes in times 100%. Now what this means is if the efficiency is 100%, that means that the heat that comes out has to be 0. That makes sense? In other words, all the input heat is turned into work. The problem is that's impossible. It cannot be done. The second law of thermodynamics, in fact, can be expressed in a number of different ways, but one of those expressions is that no engine is possible where the heat that goes in is entirely converted into work. There was a French engineer by the name of Sadi Carnot that came up with the idea of what is now known as the Carnot engine. There's a picture of him, dashing fellow, don't you think? It's the most efficient heat engine imaginable. Notice I didn't say it's the most efficient heat engine possible. It's the most efficient one imaginable. In that situation, Carnot discovered that the efficiency of his engine, we call that E sub C for Carnot, is 1 minus the temperature of the output divided by the temperature of the input heat. Notice that those are not Q's, those are T's. Even in that case, the efficiency can't be 100% unless the output temperature is absolute 0. Yeah, remember these temperatures are on an absolute scale like Kelvin. Okay, so you can't possibly have an engine have heat go into it and remain at absolute 0. And so even the most efficient engine imaginable cannot have 100% efficiency. It depends on the temperature of the input and output heat. Okay? So let's take a look at an example of an engine called the internal combustion engine. This is the kind that operates inside most people's cars unless they have an electric car. The internal combustion engine has multiple strokes and it has valves at the top. The blue stuff up here at the top, that's the fuel and air mixture that's going into the engine. So when this valve opens up, fuel and air go in as the piston moves down, so it sucks the fuel-air mixture in. Then the piston goes up as the shaft continues to rotate, and that compresses the fuel and air. And at that point, once it's past being at its maximum height so that the shaft is a little bit bent over this way again, the spark plug ignites and there's an explosion, and that explosion causes a tremendous amount of heat energy that's converted into mechanical energy by pushing hard down on this piston, causing the shaft to accelerate. And then on the next upward stroke, the hot gas goes out through this valve. That's the exhaust. That's Q sub L. So let me see if I can get this thing working again. And there we have it working again. Though it's moving a little fast, you can see it's the intake stroke, compression stroke, power stroke, and exhaust stroke. And it's doing essentially what I said. And that's how the internal combustion engine works. Now that rotating cylinder at the bottom becomes a shaft that's attached to the transmission that goes to the wheels and makes the wheels go round and round. So that's how the internal combustion engine works. How do we make cold things colder? That seems like an unrelated question, but it actually is related very well to this whole concept. We use what's called the refrigeration cycle. There are a lot of cycles involved here. Let me show you what I mean. Before that, let's describe why it's difficult. Okay? Heat always travels from hotter objects to colder objects. Make sense? Okay? When you put a cold object next to a warm object, the heat energy travels from the warm to the cold. So how do you make a cold thing colder when it's not in contact with anything that's colder? That's the trick, and that's where we use the refrigeration cycle. Here's the idea. We have a fluid called a refrigerant that's circulating through the system. So it circulates around and around this way. Let's see what happens. Well, we have a low pressure vapor that goes into a compressor and turns into a high pressure vapor. Because the compressor did work on the gas has more energy and it's hotter. And so that hot gas goes into something called a condenser, okay? And if we're talking about air conditioning, this would be outside of your house where that big fan is, in what you think of as the air conditioning unit. Air is blown across it and carries some of the heat away, because the outside air might be 85 degrees, but it's a lot cooler than this very high pressure hot vapor that's running through it. And so the ambient air takes away some of the heat energy and causes the high pressure vapor to condense into a high pressure liquid. And that phase change from vapor to liquid requires the giving up of a lot of energy to the air. So that's why you have such hot air coming out of that outside air conditioning unit. And so it's phase changed into a liquid. This dryer is just removing any water that's in the system. And that high pressure liquid goes into an expansion valve. And what that does is it allows it to expand. And when a gas expands, it does, or a liquid turns into a gas and expands, but in this case, it's still a liquid. It's under much lower pressure, which means it's done the work. And so it loses energy and it gets very, very cold, much below the temperature of the air inside your house. Now, by this time, okay, in here, we're inside the house. And so this cold liquid goes into what's called an evaporator. And now air from your house is blown across that very cold liquid, and the liquid evaporates, another phase change from liquid to gas. That takes a lot of energy. So it's taking a lot of energy from the air that's inside your house in order to evaporate back into a vapor. Okay? And now it's a low pressure vapor, not quite as cold as it was before, goes into the compressor. The compressor puts it under high pressure, and it takes the heat outside the house again and blows air across it again to cool it off. And so what's happening is, as a cold liquid and vapor, it's removing energy from inside the house. As a high pressure, very hot liquid and vapor, it's putting heat out into the environment as environmental air is blown across it. So it's removing heat from the house without removing air from the house. Pretty cool, huh? Ha, 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 ha. This is how refrigerators work. The difference is this part, instead of being your house down here at the bottom, is the interior of the refrigerator. And this part, instead of being outside the house, is your kitchen. So a refrigerator is an air conditioner where it blows the heat into your kitchen after taking it out of your food. So that's how the refrigeration cycle works. Now, how is that related to motors? Well, let's draw a picture here. Let's suppose this is the refrigerator right here. Okay, only now you have to put work into it. Okay, and low temperature heat goes into it, and high temperature heat comes out of it. And guess what that high temperature heat is? That's going out into the environment. The low temperature heat is coming from your house, and the sum of these two is equal to this one. It's still QH equals QL plus W. Only now the work is being done by the compressor. So there's always work involved, and we always still conserve energy. And that's how the refrigeration cycle works.